Hi guys, this is Mrs. Allison. Today we are going to look at limits involving infinity as well as limits of absolute value. So let's go ahead and get started. So let's talk a little bit about infinity and what that means. Because when we take the limit of a function at infinity, what we're really interested in is the end behavior. Like what happens at the end of the graph? As the graph goes to infinity, what is happening at the end? Which can be pretty easy when we go and look at polynomials that we maybe know what end behavior looks like. So for example, if we look at this first example here, this is the one that says the limit as x, the limit as x approaches infinity of 3x to the fifth minus 4x cubed plus 11. Think about what that looks like. It's a polynomial. And when we consider a polynomial and the end behavior that happens, really all we're concerned about is this highest degree part of the polynomial. Because if we look at this polynomial happens to be an odd degreed polynomial and an odd positive. So we know that whatever happens in this graph is doing something like this. So what would the limit be as we approach infinity? It should be infinity, right? The graph should be going up. Okay. So using that same logic, what would this next part B, look like? If we are taking the limit as x approaches negative infinity this time, see the negative in there, of 3x to the fifth, what happens? Well, this is the same graph, so we're looking at the odd positive function, and therefore the limit as x goes to negative infinity as we come down over here. The limit as x goes to negative infinity is going to be negative infinity. Great. Well, what happens when it's not as straightforward? Maybe we don't know a picture of the graph. Well, we can use some algebraic techniques to go through the idea of the limit. So for example, if we look at the limit as x approaches infinity of e to the negative x, maybe think about rewriting this to look like the limit as x approaches infinity of 1 over e to the x. Might be easier to see. And if we think about 1 divided by a number that's just getting enormously large, what happens? Well, the limit is going to be 0. Okay, 1 over a very big number is 0. So let's look at this again. If we look at this as x goes to negative infinity, the limit as x goes to negative infinity of e to the negative x. Same problem. Maybe don't need to rewrite this one this time, because what happens? If I substitute in infinity, which seems kind of silly, we really are not plugging in a number per se, this would be e to the negative infinity, which means we'd have e to the positive infinity, because a negative and a negative cancel out. So then the end result is that my function is going to infinity. Okay, so let's talk about this next one, the limit as x approaches infinity of sine of x. What do you think? Think about what happens in the end behavior. Is there a way to find the limit of this? And the answer is no. This actually does not exist as a limit, because this is the sine function. The sine function we know just keeps oscillating back and forth, and there's no number it narrows in on as we get to infinity, despite what my graph just looked like back here. Okay, so let's look at the next one. This one actually happens to be a property that you're going to want to know, or should already know. The limit as x approaches infinity of sine of x over x. Anybody know what it is? The answer to this one is 0. If you want to look at an example of why this is the case, if we look at just the sine of x initially, we know that sine of x is that periodic function where it's oscillating and it goes from negative 1 to 1. So we could rewrite this negative 1 is less than or equal to the sine of x is less than or equal to 1. But my problem was sine of x over x. So if I divide everything by x and then look at each of these limits, if I look at, let's change the color just a little bit. If I look at the limit as x approaches infinity of negative 1 over x, I get 0. And if I look at the limit as x approaches infinity of 1 over x, I also get 0. So therefore, the limit as x approaches infinity of sine of x over x, right here, has to be between 0 and 0. What falls between 0 and 0 is 0. Okay, well, what about these ones? These polynomials that look a little bit messier. They actually happen to be rational functions. What can we say about the limit as x goes to infinity of these? We have 2x squared minus 3x plus 4 over 3x squared minus 9x plus 5. Well, one way that we can go about looking at this is by simplifying this problem just a little bit by dividing by the highest degree. This is just one method. So let's look at what that looks like. And if I divide everything in this problem, I'm going to divide everything in this by x squared on both the top and the bottom. So we get the limit as x approaches infinity of 2 minus 3 over x plus 4 over x squared over 3 minus 9 over x plus 5 over x squared. And if I take the limit as x approaches infinity of all of this, think about what's happening here. This limit is going towards 0, and this limit is going towards 0, and this limit is going towards 0, and this limit is going towards 0. So in the end, my limit here as x approaches infinity is just 2/3. Well, we can use something dealing with the end behavior. And if you think back to pre-calc, probably algebra 2 trig even, when we talked about end behavior of functions, one of the things we looked at was the ratio of the coefficients of the polynomials in the numerator and the denominator. So we can use that as another idea. If you remember, when we did that, if the degrees of the numerator and the denominator were the same, it was the ratio of the leading coefficients, 2/3. Okay, let's go back and do the limit again of this next problem. Notice it's a very similar problem. This time, though, the degrees are a little bit different. So 2x squared, 3x cubed. I'm going to look at just these. Here's why. I know that regardless of what happens, if I divide everything by x squared again, and we go through that same process, what's going to end up happening is that these terms are going to go to 0 because we're going to have a number in the denominator of those fractions that are smaller than, that are really big, get really big as we go to infinity. So really what I'm looking at here is I'm looking at the limit as x approaches infinity of 2 over 3x because I can reduce the exponents. And what is that limit? Well, that limit is 0. Okay, so let's go back to the trig pre-calc, the algebra 2 trig, whenever you talked about those end behaviors. If we look at this, we know that anytime I talk about what we called horizontal asymptotes, is that when the degree of the numerator was less than the degree of the denominator, the end behavior was going towards 0. Well, do you remember we didn't talk about end behavior really as much in algebra 2 trig pre-calc? We talked about asymptotes. So let's talk about the idea of asymptotes and then let's look at how that helps us. Okay, if you remember, asymptotes, let's change colors here. Asymptotes, we had two types, vertical asymptotes, horizontal asymptotes. And really, horizontal asymptotes are just a name we made up to describe end behavior because we were already talking about vertical asymptotes. A couple things you need to know. Vertical asymptotes represent a discontinuity. So vertical asymptotes are a discontinuity. It's any time we have some polynomial function, some number, divided by 0. Okay? So anytime we have a function divided by 0 or a number divided by 0, we get a vertical asymptote. And here's what we know, is that if I'm taking the limit as x approaches some number a of a function, and the result is n over 0, whatever the number is divided by 0, then we know that that x equals a is a vertical asymptote. I'm going to abbreviate vertical asymptote as VA. Okay, well, how are horizontal asymptotes different? Recall, horizontal asymptotes are end behavior. It's what happens as the graph goes on forever, as the graph kind of levels off towards the end. Okay, here's what we know. Horizontal asymptotes, because they are the end behavior, are related to the limit as x approaches positive or negative infinity of some function, and we're going to get a number c, or a value c. If we get a value c, then y equals c is my horizontal asymptote. Okay, so let's try a couple examples. I'm going to move the problems up. If I want to evaluate each without a calculator, I need to look at what is happening or what I know to be true about this particular function. So for example, in this first problem, I'm trying to take the limit as x approaches 1 from the right of x minus 1. Okay, well, ignore the 1 from the right for just a moment. Okay, ignore it for just a second and think about what's happening. Well, what do I know about x minus 1? I know that x minus 1 makes the denominator 0. So if I were just to plug in 1, not 1 from the right, just 1, okay, so let's rewrite this. Let's do the limit as x approaches just 1. If I do that, I would end up, of x cubed plus 1 over x minus 1, I would end up with 2 over 0, which we know does not exist. And since it does not exist, we know that x equals 1 is the vertical asymptote. Okay, because we got a number over 0. So x equals 1 is a vertical asymptote. Well, then I can use that idea and say, okay, since I'm looking at the limit as x approaches 1 from the right, which way is this graph going towards the right as the graph moves towards the right? And if you can picture it, you could even plug in the number 2. Where is it? Is 2 big number or small number? Is it getting bigger or smaller as we get closer to 1? And the answer to this one is that the answer is infinity. Okay, try the next one. See what you can come up with on your own. Hit pause and then come back. All right, hopefully you had a chance to look at this one. It's a little bit uglier. It's got trig functions, but that's okay. We can still do it. So we're looking at the limit as x approaches pi from the right. So if I ignore the pi from the right bit for just a moment, and I plug in just pi, we'd end up with pi over sine of pi, and sine of pi is 0, which means this wouldn't exist if I didn't have that from the right piece. Okay, if that piece wasn't there. What we know then is that x equals pi is a vertical asymptote. Okay, so then if I were to go back and consider the limit as x approaches pi from the right of x over sine of x, okay, what is happening around that asymptote? And what we know is this is going towards negative infinity. All right, let's work at finding all the asymptotes, horizontal and vertical. Do you remember the process through this? Okay, the best way to go about this, especially the vertical ones, if we're not using limits to begin with, is the vertical ones we're looking at the denominator, and we need to factor. Okay, so the first thing we want to do is factor this problem. And so we get x minus 2 over x minus or plus 3x minus 2. And when these factor, we know that because these are both the same, that we now have a whole when x equals 2. And so my reduced function is 1 over x plus 3, right? So I have a vertical asymptote then, where? I have a vertical asymptote when x equals negative 3. Can we verify that taking the limit? Sure. If I were to take the limit as x approaches 3, negative 3, what I believe my vertical asymptote to be, of x minus 2 over x squared plus x minus 6, what I'm going to get is I get negative 5 over 0. That was exactly the recipe to be able to say that x equals negative 3 is my vertical asymptote. Okay, well, what about a horizontal asymptote? Remember, we're looking at the end behavior. We're looking to see what is happening. And again, in the end behavior, I can use the reduced function, or I can just use the function as it stands. And let's change colors. Let's do this one in green. If I look at x over x squared, that's all that really matters in my end behavior. If I look at those two, I am looking at x over x squared to give me 1 over x. And if I take the limit as x approaches positive infinity of 1 over x, what do I get? Well, I get 0. And if I take the limit as x approaches negative infinity of 1 over x, what do I get? 0. So I know that my horizontal asymptote in this problem is y equals 0. All right, take a second and try the next one and see how you do. Okay, looking now, let's cruise through this one just a little bit. Vertical asymptotes, I'm going to factor. And in factoring the top of this one, I get multiplies to negative 6. So we get 2x plus 1 times x minus 3 over x plus 2x minus 2. And since I don't have any holes, I know that I have vertical asymptotes, when x equals both positive 2 and x equals negative 2. Plus or minus 2 is fine. So looking at my horizontal asymptotes, again, I'm going to consider my 2 degrees. And I know those 2 degrees, my end behavior model, indicate that I have 2x squared over x squared, which gives me 2 over 1, 2. And if I take the limits, both positive and negative, as we approach infinity of 2, we get 2. And the limit as x approaches negative infinity of 2 is 2. And therefore, I have a horizontal asymptote at y equals 2. Feel pretty good? Okay. Okay, let's review the absolute value function. What does it look like? What is it? If you remember the absolute value function, I'm kind of getting tired of these colors. Let's go red. The absolute value function is the function f of x equals the absolute value of x. You may even be able to visualize it as this v that looks like this. Okay. Do you remember what it looks like as a piecewise function? There are a couple ways we could write this, but what we're going to look at is that the absolute value of x as a piecewise function looks like this. X, if x is greater than 0. 0, if x is equal to 0. And negative x, if x is less than 0. We're going to use this, okay, when we go to evaluate limits for absolute value. Okay, so the first thing we want to do when we're looking at limits of absolute value, this says the limit as x approaches 0 from the right. What does that mean? Well, if we're approaching 0 from the right, it means that x is greater than 0. And if x is greater than 0, it tells me that I can replace the absolute value of x with just the function x. So this problem, in fact, becomes the limit as x approaches 0 from the right of x over x, which equals 1. Okay, try the next one. What do you think it is? Hit pause if you need to and then come back. Okay, once again, we're going to look at this idea of x being less than or approaching 0 from the left. What does that mean? Well, it means that x has to be less than 0, and if x is going to be less than 0, I'm going to replace any absolute value with negative x. So let's go ahead and rewrite my limit. So this would be the limit as x approaches 0 from the left of negative x over x, which would be negative 1. Okay. Now, combining those two, this next problem says the limit as x approaches just 0. Not 0 from the left, not 0 from the right. What has to be true about the limit at 0? Remember, it has to agree from the left and the right. Does it agree? And the answer is no. So this limit does not exist. Does not exist. One of the things you want to know is in WebAssign, D and E needs to be capitalized with no spaces. It'll make your life a little bit easier. Okay, so the left limit does not equal the right limit, and therefore the limit does not exist. All right, try the next one. What do you think? Okay, this limit is 1. Because we can just substitute in 3. 3 doesn't cause any problems. It doesn't give us any issues. Absolute value of 3 is 3 divided by 3. So the limit as x approaches 3 is 1. Okay, so let's look at some more fun examples. This last example, I said some more, but I only mean one. This last example actually comes up fairly regularly on the multiple choice part of the AP test, usually in the AB subsection, but this is what it looks like. Something like this. Okay, a couple things to notice. This says the limit as x approaches -2 from the right, and you'll notice that in this denominator there also happens to be a value that would cause it to be 0. -2 would make the denominator 0. Okay, so let's think about what this absolute value of x plus 2 looks like. Maybe even we go back to the definition of absolute value, which says that the definition of absolute value of x plus 2 would be, as a piecewise function, x plus 2 when x is greater than or equal, greater than -2, 0 when x equals -2, or the opposite of x plus 2 when x is less than -2, because this is a graph that is shifted to the left 2 units. So if we look at a graph of this is an absolute value graph that looks something like this. Okay, so we can readjust our thinking just a little bit. If we see that x is approaching -2 from the right, -2 from the right would be numbers that are just greater than -2. So that would be these numbers up here. So really what I'm looking for in this problem is I'm looking at the limit as x approaches -2 from the right of x plus 2 over x plus 2, which is 1. Okay, feel free to rewatch this video as needed. It will be available on Canvas the whole time, so feel free to watch it again if I spoke too fast. Otherwise, we will see you soon.